Hello, and welcome to another lesson on the topic of Indices and Surds, pure chapter 1.3. So the previous two lessons on the Indices and Surds chapter, we've been looking at, in particular, indices. Now we're going to be moving on to looking at what surds are and how we can work with them. So before we do that, as ever, there's a selection of warm-up questions. Here they are, questions 1, 2, 3 and 4. And so if you could have a go at these, if you can, and then only play the solutions to these once you've attempted them yourselves. Okay, so what we're going to do now is have a look first of all at the solutions to question 1. So for question 1, we need to circle below any irrational numbers from this particular grid. So what we need to do is just remind ourselves of what we mean by an irrational number when talking mathematically. An irrational number is essentially a number that, if you wrote it as a decimal, would have an infinitely long pattern which wouldn't recur. It couldn't be written as a fraction. So for example, 1/3 is 0.3 recurring, but the 3 does repeat. Because the 3 repeats, it's not irrational, it's rational. Hence the fact you can write it as 1/3. So 0.1 recurring, here, that's actually the same as 1/9, and so that is not irrational. So don't be tempted to circle that one. The most famous irrational number is probably pi. Pi is irrational. As well as pi being irrational, root 2 is irrational. If you typed in root 2 on a calculator and asked for a decimal output, that would give you 1.4 and so on and so on. It wouldn't repeat in any meaningful way. Here, 0.12345, ... means this carries on. So although the pattern is predictable, it's not a pattern that repeats, because these are just for counting numbers, so the next one would be 6, 7, 8, 9, 10, 11. So there's no end to this pattern, hence it can't repeat, hence this one's irrational too. The others are rational. This is exactly 3, this is 4, that's a fraction, so it's rational. This is a terminating decimal, it does have a clear end, so although it's a decimal, that's still very much rational. Square root of 1/9 is a third, so this is minus 1/3, which is rational, and this is the same as 1/9. Part B, we're asked to circle any square numbers from the list below. And so a square number is just what we get if we take any whole number, including 0 we could define this as well, and multiply it by itself. And so we could say that 0 is a square number because it is 0 multiplied by 0. So the 0th square number, if you like, is 0. Moving on from that, we could try the others by using a process of prime factor decomposition if we're not sure. The easy one here though is probably going to be 1, and so let's just circle 1. A harder one to spot is 361. This is actually 19 squared. An easy way to do this would be to square root all these numbers on your calculator. Whichever give you whole number answers are square numbers. But I just want to link this into a numerical process if possible. So if we have a look at 729, for part B, if we think about 729, the tip here is to sum the digits of 729. These add up to 18, which is a multiple of 9. Therefore, we can deduce that 729 is a multiple of 9. So we could divide 729 by 9. You might be thinking, well, if it's a calculator exam, why do this? It's just to get you warmed into the year still, really. So how many 9's in 729? Well, we could work this out with the good old-fashioned bus stop method. And so if we just write down 9 on the outside and 729 on the inside. As I've said before, you could use a calculator if you really wanted to, but let's just test our numerical skills. So 9's into 7 obviously doesn't go, so that 7 carries over. So now I need to do 9's into 72. Well, there's exactly 8 9's in 72, because 8 multiplied by 9 is 72. So we have no remainder. And finally 9 into 9 goes once. No remainder. And so 729 is 9 times 81. Neither of these are prime. So if you remember your prime factor trees, we go again. So 9 splits into 3 and 3. Both of those are prime, so we circle those. Meanwhile, 81 is 9 squared, So we have 2 9s here, and each one of those 9s splits into 2 3s. So although a calculator could have told you this, it's nice to do some things yourself in life. We've proven that 729 is actually 3 to the power 6, which is the same as, using the laws of indices from the previous lessons, that's the same as 3 cubed squared. In other words, 729 is 3 cubed, which is 27 squared. If you square root 729, you get 27. Therefore, 729 is itself a square number. I know we're not doing part C yet, but when it asks in part C which of the square numbers are also cube numbers, well, if we think of 729, which is 3 to the power 6, we could also see this as being 3 squared cubed rather than 3 cubed squared. So 729 is actually 9 cubed. So if we were to cube root 729, we would get 9. So 729 is also a cube number. Carrying on these numbers, 8 isn't a square number. 8 is a cube number, so I could write this there, only I can't actually select it as a square number. 8 is a cube. So we had 361. We need to think about 4096 now. So if you're to do this process for 4096, what you would actually find is that 4096 is actually 2 to the power 12. So 4096 is 2 to the power 6 squared. 2 to the power 6 is 64. So the square root of 4096 is 64. And so 4096 is a square number. These are all the square numbers, in this list at least. 0, 729, 361, 4096 and 1. So of these, apart from 729, which are cube numbers, which would give us whole numbers if we were to cube root them? Well, if we did the cube root of 0, that is itself, because 0 multiplied by 0 multiplied by 0 is 0. And so we can add 0 to the list, because it's also a cube number. 361, no go. 361 is only 19 squared, it's not a cube number. 1, however, is a cube number, because 1 multiplied by itself 3 times would give us 1. And also 4096 is a cube number. 4096 is 2 to the power 12. So using the power of a power rule, we could also say this is 2 to the power 4 cubed. 2 to the power 4 is 16. In other words, the cube root of 4096 is 16. And so that also is a cube number. Moving on to question 2 of the warm-up. List all the factors of the following numbers. So 32 and 192. Now, we could just do a factor diagram, factor bug diagram for 32. So I'll do it one of 2 ways for you. So 32, put that in the middle, and then on one hand, start with the smallest number you can divide it by. On the other side, give the answer to that division. So 32 divided by 1, that's 32. 32 divided by 2 gives us 16. Can't divide it by 3, but I can divide it by 4, which gives us 8. I can't divide it by 5 or 6 or 7, but I can divide it by 8, which you've already got. And so these are all the factors of 32. I'm just going to show you another way we could have achieved this result. So we could use prime factor decomposition with a twist. And so 32 is an even number, so we can half it, which gives us 16. 2 is prime, so we circle the primes. 16 we can divide by 2, which gives us 8. 8 isn't prime, we can divide it by 2, which gives us 4. 4 isn't prime, so if we divide it by 2 again, we get the final 2 2s. And so 32 is 2 to the power 5. So you might be thinking, well, how does that help? How does this relate to that? Well, any factor of 32 must be some combination of multiples of the prime factors. And so if we play around with any of these, we could have 2 on its own, 2 times 2, which is 4, 2 times 2 times 2, which is 8, 2 to the power 4, which is 16, or 2 to the power 5, which is 32, so long as we also remember to include 1, because 1 is a factor of any whole number. So didn't really need to do that method for 32, but it's much more useful for 192. Doing a factor bug diagram for 192 is quite tedious. So let's do it via this prime factor decomposition method. So we can half 192, which you should find is 96. 2's prime, so circle that. 96 isn't, so we can half that one, which gives 48. 48 again can be halved. That's 24. Half it again, you know the drill by now, that's 12. 12 can be halved, which is 6. 6 can be divided by 2, which is 3. And so factors of 192 are now going to be some combination or combinations of multiples of these prime factors. So we've got these prime factors here. So always start with 1, because 1 is a factor of any whole number. So we can use just one of the 2's. We could use just one of the 3's, just for 1 3 on its own. Or we could do 2 times 2, which should be 4. We could do 2 times 3, which is 6. I'm going in ascending order. Or we could do 2 multiplied by 2 multiplied by 2, which would give us 8. We could use 2 2's and a 3 to give us 12. 2 times 2 times 3 is 12. Or we could do 2 times 2 times 2 times 2, that would give us 16. Or we could do 2 times 2 times 2 times 3, which is 24. Or we could do 2 times 2 times 2 times 2 times 2, which is 32. Or we could do 2 times 2 times 2 times 2 times 3, which is 16 times 3, which gives us 48. A bit tedious, I know, but it's good practice, just trust me. 2 times 2 times 2 times 2 times 2 times 2, 2 to the power 6, that gives us 64. Or we could do 2 times 2 times 2 times 2 times 2, 32 times by 3, which is 96. And finally, we could do all of these and multiply them together, which will always give us the original number itself. So 192 has a bloody load of factors. And for part B, which of these factors of 32 and 192 are square numbers? So this is a bit easier. We've done the hard work now. So first of all, let's think of factors of 32. That are square numbers, I mean. So we've got 2, which isn't a square number. 1 is, so we've got 1, which is a square number. We had 4, that's a square number. And 16. Whereas the factors of 192, which are also square numbers, we've got obviously still 1, 4, there's no 9, 16's there though, no 25, no 36, no 49. We do have 64 though, and that's the last one. And so that's question 2 done. Question 3, a bit of revision from chapter 0, expanding and simplifying. So what we need to do here is just multiply out everything on the outside of this bracket by everything on the inside. So minus 2 times 3 gives us 6, x multiplied by x gives us x squared, and then just y. Next, we do minus 2x multiplied by minus 5x cubed. Minus 2 multiplied by minus 5 is positive 10, and the x multiplied by x cubed is x to the power 4. Next along, we take the 2x and multiply it by each term in the other bracket. So 2x multiplied by x is 2x squared. We then do 2x multiplied by minus 3y. So 2 times minus 3 is minus 6, then x times y. Next up, we do y times x, which gives us positive xy. And then y multiplied by minus 3y gives us minus 3y squared. This can now be neatened up and simplified. So we have 2x squareds minus 6xy plus an xy gives us minus 5xy's overall, and then minus 3y squared. Finally, of the warm-up, question 4, what is the value of n? So this looks a bit of a weird question, but it's actually not anywhere near as hard as what it might originally seem. Let's use this power of a power law twice. So 10 cubed to the power n, and all of that to the power 2. Let's work from the outside inwards. Okay, so what we have here is 10 cubed. Now n to the power n to the power 2. This power of a power we can work out by multiplying the powers. N times 2, that's the same as to the power of 2n. Now we can do the same thing again. To the power 3 to the power 2n, we can multiply these two powers. 3 times 2n. That's the same as 10 to the 6n. So all of this here is the same as saying it's 10 to the power 6n. Now we just need to take a step back and remember the obvious thing about powers of 10. For example, 10 squared is 100. Power 2 has got 2 zeros in it. Ten cubed is 1,000. Which has 3 zeros. And so the point I'm getting at, which I'm hoping you can see as a relatively obvious one, the power of 10 tells us how many zeros are following the 1. So in this case, how many zeros is in this very long number? Let's just count them up. So they come in blocks of 3, because they're nicely punctuated. 3, 6, 9, 12, 15, 18, 21, 24 zeros. So like I've said now, the power of 10 tells us how many zeros there are. And so 2, 2, 3, 3. In the same way, 6n must be equal to 24. So using these two bits of information here, we can now say that therefore 6n must be equal to 24. The key link is making that conceptual understanding. Once you've got that, this is the easiest equation in the world to solve. Well, maybe not the easiest in the world, but it's pretty straightforward. Just divide through both sides by 6, n equals 4. And we've done the warm-up questions. Let's now have a look at the main body of lesson, which is going to be talking through surds and how to use surds. So first of all, let's just remind ourselves of what a surd actually is. So if n is a natural number that's not a square number, then any multiple of root n is called a surd. A surd is essentially a type of irrational number because the decimal expansion of it is infinite with no repeating factor. Sorry, no repeating pattern. So the most common example is probably pi. In terms of, well, the most common example of a irrational number, I mean to say, is pi. A common example of a surd is root 2. So root 2 is a surd, as is root 3, and so on. So if you've got the square root of a number which gives a whole number answer, it's not a surd. If you're square rooting a number that's not a square number, you will always get a surd. So you could use your calculators if you wished to sort these numbers into whole numbers and surds. If you did that, or even if not, you'd find that the whole numbers would be root 1, because the square root of 1 is just 1, and also the square root of 4. The square root of 4 is 2, which is what we'd expect from this definition. If n is a square number, it's not a surd. 1 and 4 are square numbers, and so these are not surds. Whereas over here, 2, 3, 5 and 6 are not square numbers, so when we square those, we would have an irrational answer, therefore these are all surds. So root 2 is a surd, root 3 is a surd, and so on. Root 5, and finally root 6. So, task for you guys now. You've got this list. You need to sort the following tiles, the 9 tiles, into numbers of 2 distinct categories. So some of these are examples of surds, some are non-examples of surds. So it's just saying which of these are surds, which aren't. So identify which surds are equivalent as well. So if you wanted to, you could use a calculator to just check this. In fact, why not? I'll show you how to do these without a calculator after, but let's bust out the calculators just for a moment. So, looking at this one. Root 3 over 5. So if we did the square root of 3 over 5, we get root 15 over 5. And so the calculator's given us a surd answer. If we try and get this in a decimal, you can see it's got no obvious pattern. And so root 3 over 5, that's the same as root 15 over 5. And so these two here are going to be equivalent examples of surds. So we can write those in straight away. If you'd like me to show you why these two are equivalent, I'll just do that for you now. So root 3 over 5, what we're allowed to do is break this surd into a numerator and the denominator. And so root 3 over 5, that's the same as root 3 over root 5. What we can do with fractions, as you remember from GCSE, is whatever you do to the top, you must do to the bottom. Or whatever you do to the bottom, you do to the top. So let's now multiply top and bottom of this fraction by root 5. And if we do that, the bottom would become root 5 times root 5, which is just 5. If you square the square root of something, you just get the number itself. Meanwhile, root 3 times root 5 is the same as the square root of 15. So that's why these two are equivalent. In the middle, at the top, we've got root 16. The square root of 16 is 4, which is a whole number. So root 16 is definitely not an example of a surd. Over here, root 2 times root 8, that's the same as the square root of 16. When you've got a surd, and it's the same root, because in this case both of these are the second root, both of these are square roots, we can combine the number or numbers underneath the surd. So 2 times 8 we can put underneath this square root symbol. Square root of 16 is 4. So that's why this is a non-example of a surd. We also have root 16 at the top here to consider. So root 16 is fairly obviously, I hope you'll understand, 4. So we've got root 16 there. As is, like I said here, root 2 times root 8. So both of these, which are equal to the same thing, are non-examples. They're equivalent, but we don't need to label this because we just need to think about which surds are equivalent. So we've got root 16 and also root 2 multiplied by root 8 as non-examples, which happen to be equivalent, these two. Root 5 squared. Root 5 times root 5 would be exactly 5, and so this again is an example of a non-surd. Root 2 is irrational. So root 2 itself is a surd. So 10 multiplied by a surd we could also class as a surd 2, and so this itself is a surd, which is 10 root 2. That would have an infinitely long, non-repeating decimal pattern, hence a surd. Root 200. Well, let's think about what root 200 means. Now, with surds, we can alter surds into different equivalent forms by finding square roots of the number inside the surd and splitting the surd into multiples of a square number. And so root 200, for example, square root of 200, well, 200 is 100 multiplied by 2. Why did I say 100 times 2 instead of, say, 4 times 50? It's because 100 is a square number. And so if I rewrite this as root 100 root 2, then we can then square root the square number. So root 100 root 2, square root of 100 is 10, and we can leave root 2 on its own. But we saw 10 root 2 over here, and so actually this one, root 200, is 10 root 2 in disguise. So these two are not only surds, but are also equivalent. And so 10 root 2 equals square root of 200. So we've done 1, 2, 3, we've done these ones. So we just need to look at these bottom two on the left and right to decide if these are surds or non-examples of surds. Well, here we have root 25. Root 25 is 5, and so this would equal 3 times 5, which is 15, which is a rational natural number, certainly not a surd. And so 3 root 25 is certainly not a surd. In the same way, really, 36 over 81, both of these are square numbers, and so if we square root 36 over 81, that's the same as the square root of 36, which is 6, over the square root of 81, which is 9. So this is 6/9, which is obviously 2/3. And 2/3 is a rational number because it can be written as an exact fraction. So this too is a non-example of a surd. As a double check, there were 9 cards to sort. 1, 2, 3, 4, 5, 6, 7, 8, 9. We've sorted them all, and more than that, sorted them all correctly. So let's have a look at some worked examples. So this first set of worked examples, we're going to be simplifying surds. The trick here is, well, without using a calculator, of course, the calculator can check to see your answers are correct. The tip here is to try and find a square number, the biggest square number you can, in fact, that is also a factor of the value inside the surd. So like we saw in the previous task with root 200, the biggest square number that's a factor of 200 is 100. And so we can just rewrite for a second root 200 as 100 rooted multiplied by root 2. We'll leave root 2 as it is, and the square root we just simply square root. So square root of 100 is 10. Root 2 is just root 2. And so square root of 200 just becomes 10 root 2. We use exactly the same idea now for part B. So for part B, what's the biggest square number we can find which is a factor of 32? Well, there's various square numbers that are factors of 32. We've got 1, 4, and 16. The biggest of those is 16. And so what I'm going to suggest we do is we rewrite 32, the square root of 32 rather. We break the 32 into 16 times 2. In the same way, root 32 becomes root 16 root 2. And root 16 is just 4, and so we end up with 4 root 2. You may be wondering, well, what would happen if I picked the wrong square number? Like, no need to panic. For example, if you were to pick a smaller square number and didn't spot that 16 was the biggest square number you could pick, you wouldn't need to panic too much. It'd just take you longer to get the fully simplified answer. And so, if, for example, if you thought, well, root 32, well, 4's a square number. So you might have wrote it as root 4 root 8. So root 4 would be 2. We'd end up with 2 root 8. So that isn't the same as 4 root 2. However, If you then thought about 8 itself and thought of factors of 8, you'd then also hopefully spot that 4 is a factor of 8. And so as long as you think to carry it on, you could split this 8 into a 4 and a 2. So root 8 becomes this. 4 is another square number, and so root 4 would be 2. And so this would become 2 times 2 times root 2. 2 times 2 is 4, root 2 is just itself. So you would eventually end up with the same, but as you can see, by picking a square number that's not the biggest square number, the process just becomes much more drawn out and longer without needing to be. So always be careful to pick the largest square number you can. Part C, the square root of 192. Now again, what you'll see in these worksheets and the classes is often, not always, but often the warm-up questions will help you in the worked examples within the lesson. And so if you have a look at the warm-up examples, we did factors of 192. And what we found with 192 is that there are some square numbers that are factors of 192. The biggest such number, which is a factor of 192, is 64. Okay, 64 times 3 is 192. And so we can rewrite the surd part of this as 3 lots of root 64, all divided by 2. Because, oops, need to get this like so. Because root 3 times root 64 would give us root 192. Okay, so now we've got this, we can then go forward and simplify further. So here, root 64 would be 8. So we'd end up with 8 root 3 all over 2, and then 8 over 2 just gives us 4. So we end up with 4 root 3. Here, you now have a task to do on your own. You can work with a partner you sat next to, of course, if that's what you want to do. So what we need to do here is identify the odd one out in each row. Write down a surd in the blank box equivalent to those that are also equivalent. So I'm going to do it row by row, one row at a time. So the first one, let's have a look at row 1. So we've got root 72 first. So let's just work these out and see if we can spot which ones are the same as each other. So root 72. So first of all, let's just think of numbers, factors of 72, which are also square numbers. And so 72, the square numbers which are factors of 72, we have 4, we have 9, and we have 36. Obviously we have 1, but sectioning this off into 1 and 72 isn't going to get us very far. So 72 we can rewrite as 4 times 18, because root 72 is the same as root 4 times root 18. 4 times 18 is 72, so that's the same as 2 root 18. It's also the same as root 9 times root 8, because root 72 is the same as 9 multiplied by 8, so we can partition this root off into a 9 and an 8. Now, root 9 is obviously 3, and we can leave root 8 as root 8. So now we can actually see that we've got 2 which are the same. So we've got root 72, which is the same as 3 root 8. So we've found a pair which are the same. Let's just try as well, though, splitting 72 into 36 and 2. So it's the same as root 36 times root 2. And root 36 is 6, so that becomes 6 root 2. And if you have a look, we also have 6 root 2 here. And so because these three are the same, we know now that 2 root 6 must be the odd one out. And so identifying the odd one out, we can put a ring around 2 root 6. And looking at what we had here for root 72, we can see that root 72 is the same as 2 root 18. And so because this surd hasn't been included in row 1, we can write down 2 root 18 as another example, which is also equivalent to the ones which are also the same as each other. So the 4 which are equivalent now are these 4. Let's have a look now at the second row. So let's clear off what we've done so far and start again with row 2. So row 2, I'm going to start with root 600, and in the same way as row 1, I'm going to think of the square numbers which are factors of 600. So we've got 4, because 600 can be divided by 4. It can't be divided by 9. It can be divided by 25. 36 isn't a factor of this, nor is 49, nor is 81, but we do have 100, which is a factor of it. So first of all, let's think of root 600 as root 4 times root 50, because 4 times 150 gives us 600. And that's the same as 2 root 50, because root 4 is obviously 2. So already I can see that root 600 must be the same as 2 root 50. So I've found 2 which are the same. And so because one of matches to the other, root 600 and 2 root 50, neither of those can be the odd one out because they are the same as each other. So we've tried root 4. Let's now try root 25. So that gives us root 25. Now how many 25s go into 600? It's 24 of them. 25 times 4 gives us 100. Multiply that by another 6 gives us 600. In other words, 25 times 4 times another 6. 4 times 6 is 24. 25 is obviously a square number, so root 25 becomes 5, and we can leave root 24 as it is. So we've shown that root 600 is the same as 5 root 24, and so this one is therefore the same. Because these three are the same, by process of elimination, 6 root 10 must be the odd one out. So another surd which is equal to root 600, we've not used 100 yet. So think about splitting root 600 into root 100 root 6. That gives us 10 root 6, which hasn't yet been listed, and so we can list this as our own example of one which is also equivalent to these three. And so for row 2, we've got these three which were equivalent, 10 root 6 which I can include, and 6 root 10 is the odd one out. So again, let's use the same idea for row 3. So 108. So I can see already that 108 has some factors of it which are also square numbers. Okay, I can spot that 108 is a multiple of 4. 1 plus 0 plus 8 is 9. If the digits of a number add up to 9 or a multiple of 9, that shows it's divisible by 9. And 9 is, of course, a square number. And as well as that, 108 we can work out which is also a multiple of 36. So for this one we've got 4, 9 and 36 which go into it. And those interest us because these are square numbers. So first of all, starting with 4, we can say root 100 is the same as root 4 multiplied by root 27, because 4 multiplied by 27 is 108. Root 4 is 2, root 27 can be left as it is. So already we can see that root 108 pairs with 2 root 27. So these two are the same. Let's now try and partition this using a root of 9. So 9 multiplied by what gives us 108? It's 9 multiplied by 12. So root 9 is 3. Root 12 can be then considered as just root 12. Thinking of this as well, going further, you can see that root 12 as well has a factor which is a square number, because 12 is the same as 4 times 3, and 4 is a square number. But this comes out by considering root 36. So 108 is the same as 36 multiplied by 3. If you're not sure where these numbers come from, consider doing a factor diagram for 108 and finding all the factors manually. 36 rooted is 6, and the square root of 3 becomes the square root of 3. Just leave it as it is. And so 6 root 3 also is the same. Therefore, again by a process of elimination, 3 root 6 is the odd one out here, so we can ring that one. So we can see one which hasn't been included is 3 root 12, and so we can pop that in ourselves over here for one of our examples, which we can include in the final column. So 3 root 12. Like so. Now finally, for the last row. Now we start off with 508. Now, by process of elimination, or finding out the hard way, I'm going to show you that actually 508 is the odd one out. So you could have done this by thinking of partitions of 508. So 508 does have some numbers which go into it which are square numbers. For example, 4 would be one of them. But what I'm going to do here first of all is look at the other 3. And so let's consider, first of all, 2 root 147. 147 is 49 multiplied by 3. So I'm going to rewrite this as root 49 root 3. The square root of 49 is 7. So it's the same as 2 times 7 root 3. And 2 times 7 is 14 root 3. And so 2 root 147 matches with 14 root 3. And so those two are the same as each other. And so these two can't be the odd one out. So next along, let's just be thinking about 7 root 12 or some other examples. So 7 root 12, just to take this one, we know that 12 has a square number which is a factor of it, because 12 is the same as 4 multiplied by 3. So I'm going to split the root 12 into a root 4 and a root 3. The square root of 4 is obviously 2. So this is the same as 7 multiplied by 2 root 3. 7 times 2 is 14. So again, we get the same result here, that 7 root 12 is the same as 14 root 3, which is the same as 2 root 147. And so this one as well is the same. And so we can see here that these 3 are alike. Therefore, by a process of elimination, the odd one out here is actually this first one. So in terms of finding another one, which is not here, we just need to think a little bit harder for this one on the final row 4. So because this one, 508, doesn't match, we can think of a big number inside a root which does match. And so, for example, if we were just to take 2 root 147, don't know if that's in red, forgive me, I'll do that in a black colour. So 2 root 147, I'm going to rewrite the 2 as root 4, because the square root of 4 is 2. Okay. But now using the laws of surds, the square root of 4 multiplied by the square root of 147, that's the same as the square root of 4 multiplied by 147. And 4 multiplied by 147, use your calculator to check this, that's absolutely fine if you want to. 4 times 147 is actually the same as 588. So not 508, but 588. And so I can put this one in, which matches with the 3 which we've already identified are equivalent. So I personally think that's a good activity, gets your brain thinking hard. So those are the ones which are the odd ones out. So for row 1, it's the third one along. For row 2, the fourth column is the odd one out. For row 3, the third one is the odd one out. And for row 4, the first one, root 508, is indeed the odd one out. Another worked example. So question 2 of these worked examples. So simplify 5 root 6 minus 2 lots of root 24 minus square root of 292. So this seems quite a lot to get your head around because these surds aren't obviously the same. In terms of a exam-based question, it might be worded as show all your working clearly to stop people from just using a calculator. If it didn't, and it just said simplify this, then you could just bang these terms into a calculator. The calculator would do all the legwork for you, but at this current A level, it's incredibly unlikely the question would be so easy. So the question might be contrived to make you do this without relying on a calculator. So let's think of this now. Hopefully what you'll see is that 6 is a factor of 24. That in itself is a clue. So we could maybe make a leap of faith and be thinking, well, maybe 6 is a factor of 294 as well. So let's just check this. So does 6 go into 294? Again, I'm assuming here that the question is contriving it to not really make a calculator use be permitted. Although you could just check this on the calculator, ironically, having said this. Let's just check. 6 into 2 doesn't go. So remainder 2. 6 into 29, we can fit 4 of those. 6 times 4 is 24, which is 5 off being 29, so remainder 5. And 6 into 54, we can fit exactly 9 of those. And so root 294 is going to be the same as root 6, root 49. So let's just write this down. So we have 5 root 6. Now root 24, 24 is the same as 4 times 6. And so I can rewrite root 24 as root 4, root 6. And 294 we've established is 6 times 49. And so I can rewrite root 294 as root 49, root 6. So now let's see if we can do anything further. So just to confirm, root 24 we've rewritten in this way, and root 294 we've rewrote in this way. So 5 root 6 is just 5 root 6, isn't it? Root 4, however, is 2, and so 2 times 2 is 4 lots of root 6. So this one becomes that, and the square root of 49 is 7, and so this whole thing is the same as 7 root 6. And so now we have different multiples of root 6. 5 root 6 minus 4 root 6 plus 7 root 6. At this stage, because the surd is the same, you can treat it as an algebraic expression. For example, if you just think root 6 is x, this would be 5x minus 4x plus 7x, which would be 8x. But because we're talking about root 6, 5 root 6 minus 4 root 6s plus 7 root 6s, that would be 8 root 6s. And that's as simple as we can go here. Wrote examples set 3. So expand and simplify if possible. So again, like I mentioned, we can treat the surds as x's in algebra. So we just take it as an x and we don't try to manipulate the most simple surd any further. So let's have a go at this one. So root 2 multiplied out by 5 minus root 3. And so what we're going to do first of all, root 2 times 5 is 5 root 2. Then we're going to have minus root 2 root 3. So 5 root 2 is just 5 root 2. And then minus root 2 times root 3, that's the same as root 6. Meanwhile, over here for part B, if we expand these brackets out in the same way as we used to, we do 2 times 1, which is 2. 2 multiplied by root 3, which is 2 root 3. Then minus root 3 multiplied by 1 gives us minus root 3. Then minus root 3 multiplied by positive root 3. Root 3 multiplied by root 3 would give us 3. But because it's a positive multiplied by minus, we're going to have minus 3. Root 3 squared, remember, just gives 3 itself. So this now can be simplified. And so 2 is obviously just 2. 2 root 3 take away 1 root 3. We're just left with 1 lot of root 3 and minus 3. And so that would give us root 3 minus 1. The next and final task for you today is, I've got no idea why Mr. Brockby called it The Angry Surd. I think it's a ridiculous title, and because of that, I love the fact it's called The Angry Surd. Why is it angry? I don't know. Maybe because it's a mathematical construct and it's not alive, and it wishes to be alive. But if it thought that, then how would it think? How would it have emotions to be angry? It just doesn't make any sense. So let's stop talking nonsense and see if we can look at this and solve it. So we've got this diagram here. As you can see, it's a triangle. Find the value of A in this diagram depicting 3 points on a coordinate grid. So if we have a look here, it's not too hard to deduce that this is a right-angled triangle. And so let's just label in what we can. By the way, if you can try this yourselves first and then just play the video to see if your idea is the same as mine. So just to make sure I don't give the game away here. What else can we label about this? Well, we know this side here is 2 root 5. We could also easily work out the length of this side here. The y coordinate's gone from 1 up to 3, and so the length of this side is 2. Meanwhile down here, what's the length of this bottom side? Well, x has gone from A up to 5, and so the difference between the x coordinates is 5 minus A. So we've got a right-angled triangle, expressions for the 3 sides. I'm not going to give any prizes to anyone that spots we might be able to use Pythagoras for this. Pythagoras is the way to go, in fact. So we can use Pythagoras' theorem and say that the hypotenuse squared, which is 2 root 5 all squared, that must be equal to this side here all squared, which is 5 minus A squared, plus 2 squared. This is a slight trick question. I don't like the expression typically to say things are a trick question because it sounds like we're being paranoid. Normally questions aren't trick questions, but here, the little tip I can give you, as tempting as it is, do not expand out this bracket. Leave the 5 minus A squared as it is. Don't expand it out. If you do that, we're going to get into a terrible mess. So leave this as it is. What we can do, though, is square everything here. And so 2 root 5 all squared. 2 squared is 4. Root 5 squared is 5. So this becomes 4 times 5, which is 20. As I say, leave this as it is, and just say it's equal to 5 minus A all squared. Then plus 2 squared is just plus 4. Rearrange, so we've got 5 minus A squared on its own. We have 5 minus A all squared is 16. Now you see, because this is a perfect square, we can square root it now. and get that 5 minus a must be 4. If you write that in class, I'm not going to apologise for shouting or getting really annoyed. It's not equal to 4. It's plus or minus 4. When we square root, we need to consider both positive roots and negative roots, and then analyse after if we're interested in one, both, or none. So, thinking of it as just plus or minus, we can therefore say that a is either going to be 5 plus 4, which is 9, or 5 minus 4, which is 1. So a must be either 1 or 9. But just look at this diagram and apply some obvious common sense. A is on the left of this point here. So a can't be 9, because 9, 1 would be somewhere over here. Because a is to the left of 5, a must be 1. And so what we need to do is reject the possibility of it being 9. So we can just say, so a must be 1. If you want a justification, just say something like from inspection of the diagram. But it's pretty obvious that it can't be 9. So in case a question asks you, deduce why 9 can't be a solution, or say why there's only one solution to this quadratic, it's because of the diagram. It's because from the geometry of the diagram, we have to reject the option of a being 9, because it just can't be. So that was quite a lengthy discussion of these examples, so it's now once again over to you. So on page 13 of your blue books, you will find exercise 1E lying in wait, wanting to be done by you. So don't disappoint the exercise, do it, and attempt every question. If you get stuck on the questions, you should hopefully be getting to know the drill by now. Self-assess the solutions using the back of the book, and then make corrections. If you're not sure you've gone wrong, check with a peer, check with a classmate, or ask me, either in class, on an email, or in the comments section on this video. So plug away, keep working hard, and thanks for listening. I'll see you again in class, or I'll hear from myself again in the next video. Bye for now.